So now we are in the second section of this week, where we will be seeing fraud detection from the lens of supervised learning. Okay, so I assume that most of you who are taking this course are already aware of what supervised learning is, but just for the sake of completion, I'll just try to give a simple example or simple definition of what supervised learning is all about. So in a supervised learning setting, you try to create a machine learning model with some kind of a target or some kind of a supervision. Okay, it could be the labels that you use to train a model. So there is a dependent variable and an independent variable. We will be training the model with the help of that dependent variable. So it could be as simple as, let's say that you have a image, um, and you want to classify if the image has a cat in it or a dog in it. Okay, so you have hundreds of images, and for each of these image you know what the actual output is. For each image you know if it is a cat or a dog. So this forms the labels or targets in this example. And there could be another example from the context of natural language processing, where let's say that you have a sentence, you have a text which is about a review of a movie, and you want to know what type of review is it, whether it's a positive review or a negative review, and you have the label already, which in this case, whether the sentiment attached to this text, whether it is positive or whether it is negative. And you have say hundreds and thousands of texts with the actual labels which is positive or negative. Okay, so in this case, this serves as a supervision, or this serves as the target for building the model. So that's the whole idea of supervised learning. Yeah, so now let's see fraud detection from the lens of supervised learning. Okay, so when we start seeing fraud detection from the lens of supervised learning, we make a strong assumption that the type and the nature of fraud is known to us a priori. Okay, just to give an example, let's say that you are building a transaction level fraud detection system. Okay, for every transaction you should be knowing if the transaction was fraudulent or not. Okay, so this idea of knowing if the transaction was fraudulent or not is mostly a post mortem analysis. Okay, when you start building a system, let's say you build a payment gateway and you are um, allowing payments to pass through your system. Let's say after a month you have enough data, and with the data, let's say there is some kind of uh, um, uh, information that you have to label each of these transactions as fraudulent or not. Let's say that sometimes the customer, they themselves call the financial institution and tell that these all transactions are performed in my account, but I didn't authorize these transactions, it is a fraudulent transaction. So like this, you'll be having some kind of information to tag every transaction whether it's a fraudulent transaction or not. Okay, so that serves as a label for you. So you basically know the type of fraud that happened from the data that you have, and you train a model with this fraud information that is already there. Okay, so that is the idea of seeing fraud detection from the lens of supervised learning. Of course, there could be a system where you don't know the type of fraud altogether, and you just want to detect if any transaction that is coming into my system, if it is a fraudulent transaction or not. So that is the focus of the next section. But as of now, we are just going to assume that you have some information that helped you to label the data. By labeling, I mean providing the targets for every transaction. Okay, so all the examples that I am making here will be with reference to transaction fraud system. That will be a reference, and we will just go back to this example just to draw some parallels, and that will help you to understand the system better. So some of the potential issues that we encounter when we start seeing fraud from the lens of supervised learning is class imbalance. Okay, so this happens because fraud is not very prominent in your transaction system. So let's say that you have a transaction system, and let's say per day you are processing millions of transactions. and definitely in that millions of transactions that you're processing, the fraud rate is not going to be as high as 20% or 30%. Most likely that's not the case. The fraud rate will mostly be as low as 1% or even less than that in many cases. But since the number of transactions are huge, even if fraudulent transactions are 1%, that 1% amounts to a huge sum. So that is what class imbalance is all about. The balance between the positive classes, which is the fraudulent transaction, and the negative classes is going to be heavily skewed. Um, and that calls for special modeling techniques or some tweaks that we have to do in modeling to handle this class imbalance. Okay. I mean, when you have this class imbalance issue, um, accuracy is definitely not a good measure to look at the model. Why I'm saying that is, so let's say that there is 1,000 transactions happening via a banking system, out of which there are only 10 fraudulent transactions. Okay, so the fraud rate will be 10 by 1,000. Okay, and let's say that you build a fraud system that is just going to flag all the transactions as genuine transaction. Okay, it's not going to say these transactions are bad. All transactions are flagged as good transactions. So in this case, what is going to be your accuracy? Okay, accuracy is just going to be 99%. The reason being, um, you have got 990 transactions correctly labeled out of the 1,000 transactions. Okay, so this results in an accuracy of 99%. But do you think this makes any sense? No, right? Because basically you are not saying any transactions as fraud, but your model accuracy is 99%. But that is not what you wanted. You are missing out on all the 10 transactions that are classified as fraud. So definitely accuracy is not a good metric when we start looking at class imbalance problems. So we'll see what are the metrics that we can focus on in the upcoming slide. Okay, and the second type of issue is when we start looking at supervised learning problem, we are limited to only a particular definition of fraud. Okay, so sometimes what happens is there could be many frauds which get unnoticed. Okay, and if the fraud is unnoticed, definitely in the data set whatever you have, those transactions will not be marked as fraudulent transactions. Okay, they will be tagged as genuine transactions because due to some reason the transactions were completely missed, or the tags for those were missed. It could be because of the fact that customer fails to intimate the bank, or the customer, they themselves are not aware of this kind of fraud happening in their account, so on and so forth. So if you're going to see fraud from the perspective of supervised learning, you will be limited to a particular type of fraud that happens. So if there are any new type of fraud that happens in a system, it may make it unnoticed. So yeah, that is the second limitation of seeing fraud from the perspective of supervised learning. So now let's look at some of the model evaluation metrics which people use. So whatever you see here is nothing but the confusion matrix. So I think most of you who are taking this course are already aware of what confusion matrix is, but just I'll try to reiterate here just to make the presentation complete, and just to reiterate the importance of confusion matrix. So when you look at the model's predictions, there are two possible outcomes which your model could have. One is 50 transactions can be classified as fraud, or it can be classified as non-fraud. Likewise, the actual ground truth can also have two possible values, which is basically fraud and non-fraud. So if you do a cross between these two dimensions, the ground truth and the model's prediction, there are four possible scenarios which you can land into. So the first one is the case where the model predicted a particular transaction to be fraud, and those transactions actually turned out to be fraud. Those form the true positive segment. So here positive, I mean the transactions that are fraud, and negatives are transactions that are non-fraud or genuine transactions. Okay, so the second scenario is the flip side of it, where the model predicted a particular transaction as non-fraud, and they actually turn out to be genuine and non-fraudulent transactions. Those form the true negatives. Okay, and there are other two segments, which is nothing but there could be a scenario where your model predicted a particular transaction as fraud, but they turn out to be non-fraudulent transaction. Okay, so they form the false positive. They're actually genuine transactions, but your model incorrectly predicted them as fraudulent transactions. And again, there's a flip side to this, where the actual transaction could be a fraudulent transaction, but your model failed to flag those transactions as fraudulent, and they were classified as genuine transactions. So those form the false negative segment. So when you look at the performance metric, accuracy is simply defined as a ratio of total correct predictions which the model is making to the total predictions the model is making. Okay, so if we want to get a total correct predictions which the model is making, it is basically the sum of true positives and true negatives, which is the diagonal cells. And the total prediction which the model is making is basically the sum of all the cells that sum of all the numbers that you have in these four regions, which is nothing but true positives, false negatives, and true negatives. So that is basically is accuracy. And as I mentioned earlier, accuracy is something which one should not rely on when there is a huge class imbalance, because it could paint a wrong picture. The accuracy could really be a very good number, 99 or 99.5%, but actually the model's performance could be really bad, and we just saw an example as to how that could happen. And then we will and then the second performance metric is precision. So precision is defined as a ratio of total correct positive predictions to the total positive predictions which the model is making. So let's look at the numerator first. What does total correct positive predictions mean? So how many predictions which the model is making for positive class is correct? So they are nothing but the true positives. Okay, they correspond to the scenario when the actual transaction is a fraud transaction, and the model is also right in picking them. So those are nothing but your true positives, and the total positive predictions are nothing but the model's predictions. Positive predictions can be a true positive or false positive. A true positive is when the ground truth is also true, and false positive is when the ground truth is basically a genuine transaction, but your model was incorrect in saying that it's a fraud transaction. So basically, if you look at precision, it is the ratio of this term over here to the sum of these two. And let's look at recall now. So recall is defined as the ratio of total correct positive predictions divided by the total positives that you have in the data set. Okay, so how many of the frauds our model is able to recall correctly, is able to capture correctly, that is what is being illustrated in this recall metric. So this is defined as a ratio of true positives, which is the total correct positive prediction, which is same as the numerator of precision, but the denominator, instead of having it as total positive prediction, it is basically total positives in the data set, which is nothing but in your data set, the total positives are nothing but the true positives and false negatives. So false negatives are ones where the model was saying that it is not fraud, but actually they were fraud. Okay, so some of these two cells will give us the sum of total positives in the data set, and that is what is called as recall. So recall tends to be a good metric when you look at fraud detection. Again, there's a lot of business justification that has to be given, but in most cases recall seems to work good. Why I'm saying that is, sometimes the financial organization, uh, they are very strict about fraudulent transactions. Okay, they are okay to stop a genuine transaction, flagging them as fraud, but they don't want the other way around. They don't want a fraudulent transactions to be successful. So in these kind of scenarios where the organization is okay to stop a genuine transaction but not okay to allow a fraudulent transaction. Recall is a very good metric, because recall tries to tell you how many of the frauds were actually captured in your in your model. Okay. And sometimes there could be a little bit of trade-off which you want, which you want to do between precision and recall. So we have this measure called F1 score, which is nothing but the harmonic mean of precision and recall, uh, which is, yeah, which is 2 into precision into recall divided by precision plus recall. So yeah, so um, one could like rely on precision recall or F1 score when we uh, want to build a fraud detection model. Again, it is depending on the business, but accuracy tends to be a very bad metric. So when you try to plot a confusion matrix for the example that we saw in the previous slide, which is I'll just go back to the previous slide, which is this, where there are 100 transactions, 1000 transactions that are happening in the banking system, and 10 of which are fraud. So if you are planning to do this, and we saw earlier that the model was making all transactions as genuine transactions. Okay, so the model was not predicting even a single transaction as fraudulent transactions. So the model's predictions are 0 in both these cells. The model is not predicting any transaction as fraud. But on the other hand, um, all the 1000 transactions that were predicted as fraud, 990 of them were actually non-fraud. That's why 990 comes here and the remaining 10 goes here. So this is how you typically form a confusion matrix. Of course, this confusion matrix doesn't make much sense because the model itself is not a good model. But I'm just trying to highlight you the things that we need to understand when we try to evaluate a model. So now let's look at what is known as the model relevancy metric, and this is very essential. The reason being, this metric allows you to tell if the model is relevant in the current time or not. So let's say that you build a fraud detection model in 2020 using the data from 2019, and the model was pushed to production in January 2020. Okay, and the model was running fine for 3-4 months, and after that you see a dip in model's performance. The model that was doing good in identifying frauds was not performing as good as it was performing before. And the reason for this is, after March or April of 2020, COVID hit us, and we were in the world of lockdown, and so the nature of frauds itself completely changed. Okay, people were more into digital systems, and they were sitting in front of the computers, and the fraudsters were trying to cheat the system in a more innovative ways. So that's the reason why that could be the reason why the model started deteriorating. But your model failed to capture that. The reason being, the model was not trained to see those types of different frauds that has emerged. And this is the reason for having something called as a model relevancy metric, just to see if the model is still relevant in the current world, or do we need to tweak the model. And one of the common metrics which people use for finding out if the model is relevant or not is called as the PSI, which is Population Stability Index. Okay, so this helps us in understanding if the population that we are working with is stable with respect to the time it was developed or not. Okay, so let's say that you have the model that is developed using 2019 data, and then the model is put into production, and you take a data from say December of 2020. You are just seeing if these two data is still having the same distribution and same characteristics, or have they changed significantly. If the data has changed significantly, then definitely the model performance will be bad, because as you might be knowing, data is a key ingredient for any model building. And if your data is corrupt, or the data has changed its nature, then we have to retrain the model. So the idea of PSA is very simple. Okay, let's say you have two distributions here. Okay, the idea here is to see how similar these two distributions are. Okay, so here when I say distribution, it is a distribution of the scores. Okay, so when you predict I mean when you use the model to predict if a transaction, if it is fraud or not, you get something like a probability score that tells you how likely a particular transaction is a fraudulent or not. So basically that's a fraud score between 0 and 1. Higher the value, more fraudulent the transaction is. And you have the scores of all the transactions that happened in say 2019. Okay, and you have a distribution of it. So let's say that that corresponds to this purple distribution. Okay, and you took the data from say 2022 or 2020 December, and try to find out the scores of the model and try to plot a distribution of it, and that is what is given by this green uh, distribution that we have. So now your goal is to see how similar or dissimilar these two distributions are, and that is where we use population stability index. Okay, um, so the way we compute PSI is pretty much straightforward and simple. So I'll just walk you through an example of computing the population stability index. So first so for this example, let's take your development data is Jan to December 2019, and the this serves as your benchmark, and your the vintage for which you are testing, let's say that is going to be December 2020. Okay, so now you take all the score, I mean you take the scores of the model for the data in your development and sort it in ascending order, starting from the lowest score to the highest score. And then what you do is you do something called as deciling. So this like deciling is nothing but you just divide the data into 10 equal parts. Okay, so the first decile will be nothing but the value from 0 to 10th percentile, and then from 10th percentile to 20th percentile, that will be your second decile, and then from 20th percentile to 30th percentile will be your third decile, and so on and so forth. So for each of these deciles, you know that the number of data points falling in that decile is constant, which is 10%, but the cutoffs could slightly be different. So here I've just taken an example. So here let's say the score range for the first decile is between 0 and 0.12. Okay, and the score range for the second is 0.12 to 0.2, and likewise the uh, cutoff for the eighth decile is going to be 0.8 to 0.89. Okay, and you also find out the percentage of data that that is basically falling under each of these deciles. Okay, for development data, uh, this should be development, and this is be the vintage. Okay, cool. So the basically you're finding out the percentage of data that falls in each of these buckets. For development data, it's pretty straightforward. It is 10% of the data, because that is the very idea of doing this deciling. But the number of data points that fall in this range for first decile could be different for the vintage data, that is the December 2020 data. So within this range 0 to 0.12, find out the percentage of records that fall in this range. Let's say that that's going to be 12%, and let's say within 0.4 to 0.53 you have again 10% of the data. So if you sum this up, it's going to give you 100. Likewise, if you sum this up, it's going to give you 100. So basically you have divided the data into different buckets. So what percentage of data falls in each of those buckets, that is what you are computing here. And then once you have that, you do what is called as A minus B, and then you find out the difference between column A and B. That is what you compute here. So here it is 10 minus 12, which is minus 2. Here it is 10 minus 8, which is 2, so on and so forth. And then you perform this operation, which is you just take the ratio between A and B and then take a logarithm of that. That is what is being computed here. Okay, if you, so for this example it will be ln of 10 by 12. Okay, likewise you will be doing it here, and then here the desired psi is nothing but the product of these two. So you get 0.36 as minus 2 into minus 0.18, that gives you 0.36. So that is going to be the desired psi, and you just find out this desired psi for every desired. Okay, and once you have that, you just take a sum of for this, and that is what is going to give you the total psi of the data set that you're looking at. So this psi is a measure of how different your vintage data compared to your development data. Okay, higher the value, um, higher the difference, the data are shifted significantly. Lower the value, which means that if the data, if basically the psi is going to be very close to 0, then the data has not shifted much and we are good to use the same model. But there's a general guideline which people follow, which is basically if the psi is less than 10%, then there is no significant change to the population and we can continue to use the same model. If the psi is less than 20%, then there is something like a moderate change in the data, and if the performance has dropped, then we can choose to change the model. And if the psi is going to be more than 20%, then we say that the population has shifted significantly and it is good for us to change the model. Okay, yeah, so that's about psi. I hope this slide makes it clear. So now that concludes the theory portion for the second part. Now we will get into an hands-on session where we will try to build a fraud detection model, transaction level fraud detection model using decision trees, and compute some of these metrics that we just discussed. So I'll also tell you what are the nuances that we need to take into consideration when you have this class imbalance in the hands-on exercise. I'll see you there.